Hello, in Statistics 1 of AS Mathematics, the normal distribution is quite an important aspect. I'd like to use this tutorial video to try and show you where exactly that normal distribution comes from. And here's just some of the steps that we'll need to take in order for you to understand those. So you need to know about your histograms and frequency polygons. You need to think about what happens when we're looking at populations rather than a small sample of data. And then we'll look at something called the standard normal distribution and its features. So here we are, we're starting with histograms and frequency polygons. Here's an example of a histogram. It's essentially like a bar chart for continuous data. So you should have seen these before. What's really important about histograms though, and it explains some of the key features of histograms, is that we're interested in the shape of the distribution. In a histogram, you can see I've got these sort of bars here. They could be different widths, but they don't necessarily have to be different widths, and there's plenty of examples where the class widths are the same. In this example, I haven't got any labels for my axes. I mean, obviously we'd expect this one to be frequency density, but I haven't got any label for this horizontal axis. And so my question to you is, well, what could this be a distribution of? To give more of an indication of the shape of the distribution, I've also included the frequency polygon on here, and you can see the frequency polygon appears to be kind of joining up the middle of each of these bars. Going back to this question then, the shape of the distribution looks like to me most of my data is gathered around the middle, and then in the extreme edges I get less and less data. And if you think about that, there are millions of different situations where you get that sort of situation. Lots of data all gathered around a middle value, and then extreme values you get less and less. A typical example that you see in textbooks and things is they talk about people's height. So you get lots of people in a sort of average height, and then a few people who are shorter and a few people who are taller. The next thing I want you to think about is when we're looking at histograms and frequency polygons, when we collect the data, why do we have it grouped? Well, one of the answers is because of the accuracy issue. If it's truly continuous data, then strictly speaking, if I had more and more sophisticated equipment for measuring things, then I could never actually arrive at a value. I could just keep on going and get extra decimal places and that sort of thing. So instead of looking for actual values, it actually makes a bit more sense to group them and say, well, it's less than this and bigger than that, or something along those lines. Another really important thing is that this emphasis of the shape of the distribution. It's by gathering up my data into groups that I get these columns and the bars that are present. If I just tried to keep all my data as separate single points, it wouldn't really help me see that distribution. They wouldn't collect together in the same way that they do in their groups and their bars. But the next question, I suppose, is what if I collected loads and loads of data? What if I really went crazy and like millions and billions of bits of data? What would happen then? Would I still have the same considerations? Imagine for a particular situation, instead of taking a sample, I decide to collect all of the data. For me, I like to think of the normal distribution as something that describes whole populations. Every single bit of data is included. If that's the case, then I'd like to think about, well, what does it mean for my histogram and the groups I've got? If I go back to that issue that I was saying before then about making my distribution shape meaningful, in other histograms I have to have a decent width of a group in order to collect enough points or bits of data in each group for them to make sense. If I've got loads and loads of data though, I think I could afford to have even narrower groups and still get enough data in each one for it to be meaningful. And this is what I think it would look like if I just did the frequency polygons. Hopefully you can see that the frequency polygon gets a little bit smoother, a bit more like a curve than this kind of notchy line graph. And I think if I carried on this idea forever, so I made my groups infinitely narrow and I had lots and lots and lots of them, and I did the frequency polygon, I think I'd get something that looked something like this from that original shape. And this is a typical shape of a normal distribution, and it's often referred to as a bell curve. The distribution is symmetrical around about this mean value, and I still have this overall shape where I have hardly any data, lots and lots and lots, and then again at this other extreme hardly any data as well. So if someone presented you with a normal distribution graph a bit like this one, and not the raw data, how might you want to interpret the graph? How could you get some actual figures? By actual figures, I mean something like, you might ask the question, I don't know if this was heights, how many people are below this height? So I've marked the height with a H, and the question would be, how many people or bits of information have I got that are less than that value? To try to explain how we could arrive at some of these figures, what I'm going to do is I'm going to spend a little bit of time just showing you how there's some connected concepts to other areas of your AS Maths study. Initially then, let's look at histogram, and one thing that's really important is you should be familiar that the area of the bars is what corresponds to frequency. If you remember, I decided to make the bars on my histogram infinitely thin, and that created that curve-shaped frequency polygon. If those bars are infinitely thin, then I'm looking for the area underneath those curves to represent frequency. And this idea of finding the area underneath a curve, especially from bars of infinitely thin width, this shouldn't make you think about integration, as you should have seen in Core 2 of your AS Maths study. So if we return to this idea about how we might want to interpret the graph, if I've collected all of the data for a whole population, so something like the height of every 15-year-old in the country, do I really want actual figures? Am I really going to be interested to know how many 15-year-olds are less than 1.6 meters tall or something like that? It seems more sensible to me, more interesting, and something you could really more easily understand if we talk about probabilities. If I, instead of saying to you, this is the number of 15-year-olds that are below a certain height, if I said to you, the probability of any 15-year-old being below this height, I think that's much more interesting, and that's what the normal distribution is actually used for. One sort of happy consequence of this is that if I replace the idea of frequency with probability, then I learn something about it. If the total frequency was actually all the area underneath that curve, then if I decide that instead of frequency it's going to be probability, I now already immediately know what that area underneath the curve must be, because it's the total, and the total of all the probability should always equal 1. So here's a quick summary of those connected concepts. In a histogram, the bar corresponds to frequency. In a situation where the bars are infinitely thin, then I'm talking about integration. And if I do something that means that I can stop thinking about frequency and rather think about probability, then the total area underneath that curve would be equal to 1. If you remember, we actually said that this shape curve could represent all sorts of things. So, the obvious example was the heights of a population of people, but it could be, the heights of a population of flower. It could be the heights of a population of tree. It doesn't even have to be heights. But if you get the idea, it could be loads and loads of naturally occurring situations where you get lots of bits of data gathering around a central value, and these, what you might consider sort of outliers, these hardly any smaller values and bigger extreme values that would fit with this overall distribution shape. So if this represents all sorts of different contexts, the scale that I have on this axis here could be anything. It could be all sorts of different units. If I wanted to do an interpretation of this shape, but for, I don't know, the distance that grasshoppers can jump, or the weight of antelope, then I'd have to do something completely different each time I wanted to analyse it, and that's an incredibly large amount of integrations to have to do. What's also a bit of a downer for this is that the actual shape of this curve, it doesn't belong to, your familiar ones like x squareds or cubes or something like that. The formula for this shape, this curve, is unbelievably complicated, and for me, that consequence of having this difficult shape and having to do loads of different integrals depending on whichever value I'm interested in and whichever context I'm thinking about, that's a bit off-putting. I'd have to do lots and lots of different and very hard integrations. And to an extent, that's why we have the standard normal distribution. We have one that we're very familiar with, that we know all about, and we can use this to work out lots of information about lots of other different contexts. So in the standard normal distribution, this axis is going to be Z. I always put a little line on my Z so they don't look like a 2. And this information in this box is really important. This, if you read this and interpret it, it says Z, and then we have this line which says Z is distributed, and the N is for normally, so Z is distributed normally, and then these things in this bracket are called the parameters of the distribution, and what they are is first of all the mean, and this here is the variance. So Z is distributed normally with a mean of 0 and a variance of 1 squared, which also happens to be 1. Now I can add some of that onto the table, can't I, onto the graph. So there you go, there's my mean, 0 right in the middle. You should notice that the graph is symmetrical about that point. So if you wanted to know something about, I don't know, the probability of a piece of data that you pick at random in this standard normal distribution being less than this value here, then this is the kind of integration that you would need to do in order to find that out. And I don't mind telling you that I don't fancy doing that. So if you would like to know the probability of any bit of data you pick at random being less than one sort of arbitrary chosen value of Z, what you're really trying to find out is an area. So here I have coloured in, as best I can, the area that corresponds to the probability of the Z variable being less than or equal to this particular value. The good news is this integration, despite it being really, really difficult, has already been done. Someone's already calculated every possible integration like this for me that I might want to know. And the outcome of all these tricky integrals is actually published for you in tables. You get given these tables in your formula booklet in your S1 module exam. Right, so just before I finish this clip, I'm just going to summarise what I think we've covered. What I hope you now understand is that the normal distribution could describe loads and loads of different contexts. You often get this shape where you get loads of data collected in the middle and less at these extreme values. What we actually do with these normal distributions as well is we generally involve the whole population. So we've collected loads and loads of data, and if I were to draw a histogram, because I've got so much data, I can collapse the width of my bars or my classes in the histogram and it still has a meaningful shape. And if you look at the frequency polygon, when I collapse these groups into infinitely thin groups, I end up getting this smooth curve, and we call this the sort of bell curve shape, and it's the typical normal distribution shape. Now, as I've said as well, there's loads and loads of possible contexts that could be described by a normal distribution, and it would take an awful lot of effort to try and analyse and interpret each one of those individually, especially because when we try and find out information about it, we're having to do really quite difficult integrations, talking about areas underneath parts of these funny shaped curves. So what we've done as a mathematical community is we've got to know one of these normal distributions really well. And the one we've got is this thing we call the standard normal distribution. And this is something which is distributed normally around a mean of 0, and it has a variance of 1. And we know this incredibly well, this particular distribution. And you can look up and find out what is the probability of a value being below this, below that, and it's just written for you. What's really, really helpful about this is that we actually also know a way of translating this distribution that we know an incredible amount about onto any other normal distribution you can think of. Now, I'm going to do another video clip that will help you explain and understand how that is actually achieved. But what I want you to get from this is it's whole populations, it's this typical shape. We know this standard distribution extremely well. The standard distribution has got a mean of 0 and a variance of 1, and somebody's done all these really difficult integrals for you and stuck them in a table so you can just read them out. Okay, so this is just the first of probably a few clips about the normal distribution. Please look out for the other ones, and like I say, they should be able to help you actually use the tables and to connect the standard distribution to any other normally distributed variable that you're interested in.